I'm gonna start recording. All right, so these are going to be some of my thoughts on the most important things from playlist two. At the beginning, Professor Crawford first starts about talking about the last question about like how if a sequence is bounded and monotone, it converges. So graphically, like think about like a graph that's bounded. If it's monotone, it's only going up or down, so it's gonna eventually, sorry, eventually like hit one of the bounds. So that's why it's converging. Um, and then summation notation looks like a almost like a sideways M. And it has like the value, like the first value of n equals one, and then usually goes to like infinity or some number, whatever term in the sequence, in the series. I'm sorry. Okay, so section 9.3, the first question that's asked is when does a series converge? AKA when does that series go to an infinite number? And for a geometric series, like William, you touched on this a little bit on Wednesday, it converges like when x is basically like less than one, like the absolute value of x is less than one. Yeah, and at any point, like stop me if you want to ask questions. And then partial sums, which is just basically a piece of a series, um, a piece that you can examine and is like finite or leads to be like infinite. Sorry. He had a question of like, did a certain series converge? Basically, if a series converges, it goes to a number, a finite number. Um, I don't think we really need an example for that. But like most of
That makes sense.
playlist 2 was focusing on theorem 9.2, which is the convergent properties of series. And the first part is if series AN and series BN converge, and if K is a constant, then the series AN plus BN converges to series AN plus series BN. I think is sort of
Mm-hmm.
self-explanatory because that's like two finite numbers coming together is going to be a finite number.
Mm-hmm.
And then I'm dying. A second, a second part of that is if K and N, series K and N, um, if AN converges, then the addition of K and just converges to K times the actual finite number of the series. And that doesn't change whether or not it converges because it's simply like just a constant being multiplied. So it may change like the number, the finite number that converges to, but it doesn't change the fact that it
Mm-hmm.
converges. And then the second part of theorem 9.2 is changing a finite number of terms in a series does not change whether or not it converges, although it may change the value of its sum if it does converge. Yeah, which I just went over. Um, then the last two parts he wanted us to sort of figure out on our own. The third part is if limit n approaches infinity of the series AN and it does not equal zero, if it isn't approaching zero, the series diverges, or if limit n approaches infinity, if series AN does not exist, then the series diverges. Um, I like to think about like if something's not approaching zero, if something's approaching zero, it's leveling off no matter which direction that you're approaching it from, if you're thinking graphically. Therefore, it have to diverge. And if it doesn't exist, then it's not going towards anything. So it has to diverge. I don't know if there's like a
And
better way to explain it. Um,
I have a question.
yes.
Um, so what if the limit is not maybe zero, but it's one? So I mean, it says it diverges, but I'm picturing something with like a with like if I could draw. um, so like I'll just draw my paper. So here's one. Like the series then like goes to this one instead of zero. Oh fuck. Oh, I just cursed. I'm sorry. Let me change my background. Sorry. Um, None. Okay.
Yeah.
So like it heads towards one.
Mm-hmm.
Like this would be finite towards one, like the sum, but like it's not zero. That's why I was confused by this note. Um, or yeah, this part. the statement that he asked us to choose. I mean, to discuss. I am still a little confused on why. So a sub n, is that
Mhm.
just referencing sum?
A series, yeah. I guess, yeah, because that's
Wait,
the part that confused me the most. If it doesn't equal 0, it diverges.
yeah.
Um,
Wait.
then I guess the flip side of that is if it equals 0, then it converges.
Yeah,
Um,
but like in the videos, he had examples of like remember he had the box example, the geometric
mhm,
box, and then
mhm,
like they added up to one, the fractions, the
mhm.
partial sums. Um,
Doesn't equal
yeah, I don't know.
0. I know for if it doesn't exist, the easiest way to think of that is like a vertical asymptote. Um,
Yeah,
but
okay.
for, does anyone have ideas to
Yeah,
explain this better? If it doesn't equal 0, then it diverges. Or if the sequence doesn't approach 0, the series diverges.
Wait, so is this like with like the bounded series?
I don't
I,
know because
I
he
don't
doesn't
I don't think it's
specify.
specific. Yeah, I think it's
Yeah.
just in general terms. Yeah, I think in general terms, if a
If
series
the series,
approaches, if the limit of the number approaches infinity, or limit of the series approaches infinity, um, and does not equal 0, then it diverges. Or limit, yeah. Um,
um, wait,
yes.
yeah, it's
hold
like
on.
throwing me off.
Yeah, it's throwing me
Try to
off
think
too.
of it. Cause
Mhm.
like if this, cause if it's like the example I showed, like if the limit is not, if it doesn't limit towards 0, but it limits towards 1, like it's a straight um boundary of a axis, so maybe y equals 1, then
Well, I guess if it has a vertical asymptote, then it approaches in infinity, right? So that would make it diverge.
Mhm. Cool. You got any ideas?
Yeah, it's kind of confusing. I'm not too sure.
because like if it just, yeah.
If we're all stumped, I think we should at least have everyone else try to like ask one question, just so we're not stuck on this.
Mm.
So
Okay.
when I was looking through this, I kind of want to go back to the idea of like geometric series.
Mhm.
So I'm kind of in like a gray area about like what exactly is the distinction between like what makes a series specifically a geometric series?
That's a really good question, because I
Yeah.
have, yeah.
Because like in my notes from last week, I said that the main difference is that a geometric series is the indicator of a geometric series and is when the rule is to multiply the terms by a fixed number. But to be honest, when I saw his one example where it was a 1/2 to the n, I was kind of like confused because I thought you would
Yeah.
need an x, but maybe you don't.
Oh, I see.
I think
Yeah,
about
yeah.
geometric series as something that has an exponent because like for like 1/2 to the n, that's technically 2 to the negative n. So, and also for a geometric series, the notation that he put down was like the m thing, n equals 1, infinity, then a x to the n. So I think anything that is some sort of exponent qualifies as a geometric series, but I
Okay.
wouldn't count on that.
So does it have to be like a number raised to the n, or can it be like n raised to a number to still be a geometric series?
I think it's a number raised to the n.
Okay.
It's ax to the n. Yeah. And then because 1/2 to the n is 2
I don't know,
to.
that might have been a dumb question, but
Yeah, could it be like
That's a valid question.
it's a number raised to a variable because a variable is the one it's the thing that's incrementing, right?
Yeah.
yeah.
Okay.
Yeah, yeah. Okay.
But in his like formula in the formula within textbook for a finite geometric series, for geometric series, it's a plus a to the a times x plus a times x squared plus a times x to the whatever. But in that case, then the exponent isn't the variable. It's x is the variable.
The specific,
But isn't the exponent like the 1 or the squared or whatever? Isn't that what's increasing?
Oh,
throughout?
that's true.
Yeah.
That's true.
Yeah.
Yeah. So it's just that anything with
A is just a constant.
Mm-hmm.
Yeah, A is just a constant that like if the number isn't changing, then the A would be 1, I think. And like, yeah, because in his example in the video, he only changes the n value, or like increments the n value. Like the A value doesn't change. So like,
Yeah,
I guess that's
so the
it just
distinction is
represents
that the exponent is incrementing, basically.
Yeah. That's like the number of whatever term. Because like if it's like ax, then the assumption is like ax to the 0, which cancels out to be 1, so it'd be a, and then ax to the 1, on and on.
Okay. Should we answer the second or question 4 that he asked us? So it asks us if the series of n equals 1 has to limits from n equals 1 to infinity of a to n. If the series diverges, then the series k times a to n diverges too, if k does not equal 0.
Yeah. I think
that makes sense.
It's the opposite of like if the series converges, then adding a constant will make it converge.
Yeah.
The opposite. So if
Yeah.
adding a constant still is.
He emphasizes k does not equal 0. So say like k was 0, I guess it would just be 0. Yeah.
Or Professor, do you have it?
Sure. What was the context of this? I heard k is not equal to 0, but I don't know what we're talking about.
Yeah. So like if the series is divergent, then if the series has a constant multiplied to it, it's also divergent if the constant is not 0.
Right. So if we took a series that diverges and multiplied everything by 0,
it would just be 0.
The new thing we have is just 0 plus 0 plus 0. Like it's
okay.
It's a fairly common thing in theorems like this of like, oh, this always works unless it's 0, in which case it's dumb because it's all 0.
Yeah. We have one more question. It's about so if the limit of the series has to infinity and does not equal 0, then the series diverges. So like we were confused because like I was thinking like if the series approaches like a finite number like 1, like wouldn't that still converge? Like if it was like a
so it's the difference between the sequence converging and the series converging. So when we're talking about sequences, convergence means that the list of numbers like eventually balances out, and you use the example of approaching 1. So maybe it's doing something weird early on, but then eventually it's going to balance out and be just 1 1 1 1 1 or something close to that. The series converging is sort of a separate idea. It's saying, all right, well, what if we were to, instead what we're doing is we're adding up all of these numbers. Is our answer some finite number or is it infinitely big? And in this example where it approaches 1s, we can imagine what that sum looks like. Maybe it's like 7 plus -2 plus 3 plus 4 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. And the important part is that end, that plus 1 plus 1 plus 1 plus 1. If we've got infinitely many 1s that we're adding together, that's going to be something infinitely big.